Hello, my name is Martha Dunbar. I'm a third-year mechanical engineering student at Northwestern University, and today I would like to ask you a question. In America, in 1834, there was a fad sweeping the nation, and I'm wondering if anyone can guess what that fad was. No? No one? It was rubber. Rubber was unlike any material ever seen before. It was waterproof and stretchy and very different from the natural fiber substances that the Americans of the time were more used to. So as a result of its utility, it was used a lot in industrial parts, for valves, and to make bags, coats, and other things. But rubber had a major problem. In the summer, it would get hot and melt. And in the winter, it would harden into immovable blocks. So to deal with this problem, this aspiring inventor looked for a solution. He dedicated 5 years of his life mixing rubber with other substances, heating it up, cooling it down, spending all his money and almost going bankrupt, but eventually discovered vulcanization, or the process of stabilizing rubber with sulfur. His name? Charles Goodyear. Now, vulcanization is the reason we can use rubber in car tires, car parts, airplane tires, and medical gloves, and so many more applications today. It essentially takes the individual polymer chains which make up rubber and stabilizes them with a chemical link known as a crosslink, and the sulfur helps this happen. So Charles Goodyear obviously did not know why vulcanization worked. He was simply glad that it did. But what can we learn from this story that I just told you? Well, one, the pace of materials discovery with trial and error is simply too slow. And two, materials discovery can change the world. We know this. So today, I'm happy to tell you that materials discovery has accelerated 185 years later. We can use high throughput assays to rapidly characterize new materials. We can use advanced experimental techniques to sort of investigate these materials at a very small scale. We can model the materials with very powerful computers. And we can look to the building blocks of nature for inspiration, which is known as biomimetic design. So these last two are what I would like to talk to you today about, using very powerful computers to model and biomimetic design. Specifically, let's look at a problem from my research, which is to optimize the design of the most the most powerful underwater adhesive currently known. So this material is made up of styrene, chemical you're all familiar with in the form of polystyrene cups or takeout containers, and catechol, which is very chemically similar to the molecule which allows mussels, barnacles, and other mollusks to stick to surfaces underwater. So put together, this material is logically called polystyrene catechol. And so what I can do is, with these very powerful computers, is I can put particles that interact in physics-based ways together and investigate the mechanical properties of the material, similarly to how you can build up an entire world using individual blocks in a game like Minecraft. So with this technique, I can investigate how the material deforms under shear, as seen on the left here. And I can make it stiffer under shear by adding or taking away catechol. Additionally, I can optimize the adhesion of this material to any surface by balancing the cohesive force, the force between polymer molecules, to the adhesive force, which is the force between a surface and polymer molecules. But you might be wondering, what is the use of this outside of like naval applications of sticking stuff together underwater? Well, this material is of particular interest in assembled hairy nanoparticle systems, which is an advanced next generation polymer nanocomposite, essentially made up of, as you see in the green, cellulose crystals, which is a biorenewable, low density, high stiffness material, and polystyrene catechol, represented by the colorful coronas, which, as we've discussed before, is very cohesive. So what we can do with this material is, when it's put together, this material self-assembles into these highly ordered structures seen on the right, which increases the mechanical properties you see and allows this composite to be used in any place that plastic is currently used today, but with better materials and with an environmentally responsible procedure. So I would like to revisit the key lessons that we talked about earlier, but refresh them for the 21st century. So essentially, what I'd like you to take away from this talk, if anything, is that the pace of materials discovery can be accelerated with biomimetic design and powerful computers, and fundamental materials research, and really fundamental research of any kind, today can help solve the energy, transportation, and medical challenges of tomorrow. Thank you very much.